So I'd like you to consider that thinking is actually quite a risky process. If you're thinking about anything of significance, you're not sure where you're going to get through that thinking process. That's why you're thinking through this thing you're thinking through. Or you may be trying to solve a problem. And if it's a problem worthy of sustained attention over some time, you may not know that you're going to be able to solve it. So failure is a definite risk. So it's worth thinking about how we manage this risk of thinking. How do we generate the courage to actually engage in this activity? And I'd like you to consider two very different approaches. One, approach the problem with curiosity and playfulness. Think about things that really draw you in, that you enjoy working on. This greatly reduces the risk because if you didn't get anywhere, well, hey, I was having fun anyway. Another approach is to throw everything at the problem because you're afraid of what will happen if you don't solve it. Fear is a powerful motivator. This is often how problems get approached as well. Very closely related to this is also identifying the great opportunity that will come from solving this problem. I've grouped these latter two together. The first is process-oriented, and the second is result-oriented. And I want to tell you about a rigorous scientific study we've conducted into people approaching problems either coming from this process-oriented approach or a result-oriented approach, and what that's meant for their experiences of the process as well as what they've accomplished. And I want to tell you about a rigorous scientific study, but I can't because I haven't done it. Instead, what I can tell you about is my own experience. And so I'm here to tell you about that. I'll also tell you something about the universe. And there may actually be more than one universe, but there's definitely only one universe I can tell you about. So, as soon as I was able to read, I was checking science books for kids out of the library. I had a deep curiosity about the natural world and about astronomy in particular. By the time I was in high school, those interests had developed. I was very interested in quantum mechanics, and this book in particular had a profound impact on me. It really awakened a deep desire a deep curiosity about the fundamental nature of reality, about the fundamental laws of nature. And following on realizing that curiosity came the desire that I could actually be somebody who would contribute to advancing the frontier, to be someone who could figure out new laws. And this was really outsized. It was really I would love to be that once in a generation type figure like Einstein or Newton or Feynman. So it probably won't be a surprise to you that following on this desire quickly came great fear that there was no way I could live up to these desires. And at that time that I was having these desires and fears for the first time, this movie came out called Amadeus, which I'm sure many of you have seen. There are two important characters there. Of course, Wolfgang Amadeus Mozart and Antonio Salieri, who was a contemporary of Mozart, another composer. And Salieri, by his own description, at least in the movie, was given the great desire by God to create beautiful music. But the gifts to create that beautiful music, he felt, were given to Mozart instead. And this made Salieri very angry with God. So this really crystallized for me at the time my fears, wanting to be Mozart, afraid that I was going to end up bitter like Salieri. So right at the very beginning of my life in thinking and my life in science, there's curiosity, desire, and there's also great fear. In fact, the fear, because of that fear, I almost didn't even get started in my scientific life. So, I want to talk to you about my own experience going forward from there. One thing that I want to emphasize right from the start here is playfulness. So this process-oriented approach isn't just curiosity. Curiosity wants answers. Curiosity is not necessarily process-oriented. And I was curious from the beginning, but I needed to learn something about playfulness. So in my high school chemistry class, we did this exercise early on in the class where we were given a box that had something in it. And we could do whatever we wanted with the box except actually look inside the box. And we had to the goal was to have us figuring out what was in the box. And the point was that you could actually reasonably think about things. You could figure things out about things that you can't see, such as atoms. No one's ever seen an atom with their own eyes, but we certainly talk about them like they're real. So this is the point of the exercise. And I had no patience for this. You know, I was interested in the nature of reality. I wanted to learn about how things worked. I didn't want to be playing silly games. What I didn't realize, what I had to learn, was that playing silly games is actually how we discover new laws. This is how science is done. It's an amazing thing about the universe that we can conduct experiments, think about them, and actually discover natural laws. It's also an amazing thing that there are natural laws that are flawlessly obeyed. So about the time I was thinking about where to go to graduate school, I became aware of this fusion that was occurring between astronomy and the fundamental laws of nature, and there was this opportunity for me to combine these two interests. So people were talking about a coming golden age of cosmology where cosmological observations could be used to teach us about the fundamental laws of nature. So I was very excited to begin graduate school and to start to approach this frontier. Very excited, very scared that nothing would work out. I started work on doing some speculative playful work that I loved, and I really felt like I'm at the frontier. I'm creating new ideas. And going through that work, the conclusion of that more speculative work I engaged in at first led to me deciding that it was really too dangerous to be just engaged in this speculative work. It was a lot of fun, but I felt a great risk of my work having nothing to do with reality. So one of the reasons that people talk, though, about the Golden Age of Cosmology is because we had all this great data that was going to be coming, so that these ideas people were generating were going to be put to the test. We were going to actually make real progress. This playful work people were doing of trying to figure out, for example, are there new forces of nature at work actually creating all the structure we see in the universe today? These wild ideas that people were coming up with, this was not insane behavior, because all this was going to be tested and progress was going to be made. So I started playing around with this data, and I found that I loved analyzing the data, trying to figure out what the data are telling us about the universe that we don't know already. I liked finding out what's the story to be told, what does the community need to hear about what the data are telling us. I also engaged in figuring out, okay, what kind of data could we collect to find out more? What's the case? What kind of case can be made to support additional efforts at data acquisition? My thesis was about what we could learn about this early universe process of inflation from a cosmic microwave background satellite. And I'll tell you more about that shortly. So first, I want to tell you something about the universe, and that is that it's gone from being much simpler in the past to being very complex. And a lot of you may have noticed this in your own lives. I have. So here in the context of the cosmos, the universe used to be highly homogeneous. The density, nearly the same everywhere. So you might have an overdense region over here that's just 1 part in 100,000 denser than an underdense region over here. And over time, gravity amplified those small departures from complete homogeneity. So where you had a denser region, the gravitational force of that overdensity pulled in more matter, and then then that increased the gravitational force, pulling even more matter, sucking it out of the underdense regions, rapidly, over billions and billions of years, creating the highly inhomogeneous universe that we see today. How do we know this? We know this because we can actually directly see those simpler times. It's an amazing thing about cosmology, is that we can actually directly see these past epochs. And why is that? It's because the speed of light is finite. So it's very fast, but it's finite. And the universe is mostly transparent. So when we see light from the sun, that light took 8 minutes to get here, so we're seeing the sun as it was 8 minutes ago. Seeing light from the nearest star, that took 4 years for the light to get here, so we're seeing that star as it was 4 years ago. How far can we take this? We can take this back almost the entire history of the universe. So the universe is about 14 billion years old. We can't quite go back the whole way because there was an important transition that occurred when the universe was about 380,000 years old. At that time, the universe transitioned from being opaque, an opaque plasma, to being a transparent neutral gas, like the gas that fills this room. So we can actually see light from that time that first started traveling freely at the time of this transition. So I want to show you what that light looks like. And just to get you oriented, here's a picture of the optical sky at night. Now this light that was, so this is optical light. This is what our eyes are sensitive to, wavelengths of around 1,000th of a millimeter. If we instead look at light with a wavelength 1,000 times longer, microwave light, then we are seeing light that, for the most part, last interacted with matter at the time of this transition. So we're directly seeing the universe when it was just a few 100,000 years old. So I want you to get ready for this amazing picture that's going to come up. Ready? Well, I don't know what you were expecting. I told you the universe was very, very simple at early times, right? So the color here is indicating the brightness of the light. And the fact that we only have one color here is showing how very uniform the universe was at that time. We'll come back to this. It does get more interesting. I want to tell you, though, about some great advice I got when I joined the faculty here at UC Davis. Advice I got from my senior colleague, Professor Andreas Albrecht, about writing my first grant proposals. And he said, write about what you want to do. And that's very simple advice, but it was very powerful. I set about thinking about what I wanted to do, and what I wanted to do was play with data from this cosmic microwave background satellite that was going to be launched a year later. This was the year 2000. That launch happened in 2001. So I started thinking about all the stuff I wanted to do with this data, how I wanted to play with it, and writing about that. And I don't know if his advice helped me to win the grant, but by the time I was done writing that grant proposal and had it submitted, I was sure fired up to get to work because I've been writing about what I wanted to do. And I didn't have time to wait for the satellite to be launched. I started gathering the data that was available from ground and balloon-based observations. I stumbled across a paper about a statistical technique called MCMC that I knew would be really useful in the analysis, and I started using that, and it turned out to be just a great way to explore the data and figure out what the data were telling us. And I was having a lot of fun, and this resulted in a couple of things. One, it was the first use in my field of the statistical technique, which is now the way things are done in my field, the way these types of analyses are done. And secondly, I discovered, completely unexpectedly to me, that these data provided a very tight constraint on the age of the universe. And I wrote a paper about the age of the universe. And at the time, it was the most precise determination. And I did win the grant. And the age of the universe paper and the grant, those together, I got tenure here just a couple years after arriving. So that was, but now I do want to show you, I want to show you what the data looked like that came from that satellite. So here we saw this quite recently. If we increase the contrast so that we can see very small differences in brightness, then we get this picture here. And what we're seeing here, where it's darker is where it's dimmer. No, sorry, where it's bluer, where the light's bluer, it's dimmer, and where it's redder, it's brighter. And that actually reflects the conditions in the universe in this direction at the time of that transition. So this light's dimmer because that region was actually less dense, and this is brighter because this region was denser. This is just one small part of the sky. The whole sky has been mapped by this satellite called the WMAP satellite. And so here's the whole map of the sky. And to help you see really what's going on here, we'll cut away the top half of the sphere. So we're in the middle here, where that satellite is. And as Corey said, yes, we're thinking very big in this talk. Right? I don't think anyone's going to show a larger structure today. But this is often a confusing picture. So this is not the whole universe, right? So the universe, as far as we know, is extending infinitely. We don't see anything from out here because the light, at the time of that transition, when the universe was 380,000 years old, when it transitioned from opaque to neutral and this light was released to travel freely, the light that was released from out here, some of it happened to be going in our direction, but it hasn't gotten here yet. 14 billion years was not enough time for that light to get to us. So we're just seeing light from this region, that it's the right distance away from us, so that light's just getting to us now. This satellite here, on the scale of this, is actually bigger than our entire galaxy. So the sun and the Earth and us, we're here. This region, 46 billion light years away now. So it's amazing that we can see the universe at these early times. One thing that makes these observations particularly useful from a scientific perspective is that it's actually simple enough then that we can calculate what it should look like. And over 30 years ago, people calculated, thinking that there was no way we'd ever observe this, but they did this anyways. They calculated what these maps should look like. And they calculated statistical properties. I don't have time in 18 minutes to explain to you what a power spectrum is. This is some statistical property of the data. The prediction from over 30 years ago was that it should look something like this with peaks in it. These peaks are related to sound waves propagating in this opaque plasma. And so using the laws that we know about from experiments in terrestrial accelerators, they were able to predict this spectrum. Here's a theoretical curve in red, and the black points are inferences from the data, from the sky map. And it's an amazing confirmation. To me, it's an amazing demonstration of the universality of physical law. So I've told you some about life lived out of curiosity and playfulness, and I'd be lying if I didn't tell you that these second motivations played a role as well. I've never been able to get ready for a presentation until I was really gripped by the fear of looking like a complete idiot. And these fears also and hopes also added a special intensity to the work that was curiosity-driven. These guys didn't go away. You'll remember I started off my scientific story with both desire and great fear. And there are people in my field who I see as more talented than I am. And the accomplishments are great and they're soothing, but there's still sometimes the fact that there are people more talented than I am still feels painful. And I enjoyed the soothing nature of those accomplishments, and I think that partly as a result of that, I also started trying to get more of those accomplishments. So I moved more towards a result-oriented approach. And by 2006, something was wrong. At least to me, it was obviously wrong. I was thinking about leaving my field. I really couldn't imagine continuing along how things had been. And in 2007, as well, my personal life completely imploded. I needed a break. So I took Winston, my dean, don't listen to this. I stopped doing research for almost a year. I started connecting with family and friends. This is my sister here. I took my guitar out of the closet. I started taking voice lessons. I really started enjoying other aspects of my life. I started spending more time with these lovely fellows who are here with me today. And as many people do at midlife, I started an inward journey of analyzing the data of my own experience. And from what I found there, I started sharing that with other people. And something really amazing happened out of that, which was that other people started telling me about their experiences. And hearing from other people gave me great strength at a time when I felt very weak. I was drawn back to my academic work by the opportunity to work on these two fantastic cosmic microwave background projects. So with WMAP, we really got to see that we really could sensibly think about what was happening on the edge of the observable universe. And now we could actually use that laboratory to discover new laws, and that's what we're doing with these projects. So, will my embrace of curiosity and play lead to greater progress? What accomplishments are ahead of me? I really don't like these questions. They actually can be painful to me. I prefer, what do I want to do? What scientific questions really grab me? What work would be fun to do? So I've done my best to tell you my story, and now this professor is going to give you some homework. Study the data of your own personal experience. Listen to other people's stories, and let those stories give you the strength to find out what's true for you. Thank you.